Greetings, it's me again, and I'm talking about work. This is physics. We're in chapter 5. I'm on page 160. Alright, so follow along, open your book to 160, and let's get cracking on some physics. Force, it has to be thoroughly understood before we talk about the topic of work, because force is in work. And now, acceleration means that an object has been subjected to a force. Acceleration occurs if force has been applied. It's been applied, and then it's no longer applied. So that means that it's accelerating. Now, if you apply force over a displacement, then you've done work. So newtons are in the units for work, which are joules. All right, so work equals the product of force multiplied by distance. So if you apply force over a distance, you've done work. Force must be in the direction of the displacement, or else you don't do work. All right, so no work is done unless it's in the direction. Unless in the direction of displacement. Alright, so we're going to show an example of that in just a minute. But units for work are joules, and joules are just newtons meters. So 1 joule is 1 kilogram times meters squared over second squared. Now, the reason why it's squared is because we're adding another meters unit to a unit that already had meters in it. And you could see that it already has meters in it because this is a newton here. Power is work per unit time. Power equals work over time. So the units for power are watts. These topics are related because they all use force, which is force equals mass times acceleration. So that's why it's difficult to separate out these three topics, because all three of them are related. But you can't do any of these without energy. So we have to talk a bit about energy. And that's a difficult topic to define, because really the only thing you can say about it is the ability to do work. Well, you can also say it's a scalar. All right, so you wouldn't have energy as a vector, but you would multiply a work vector by the energy scalar. All you could really do is talk about different types of energy: potential energy, kinetic energy, which are mechanical energy, sound energy, heat energy. You could talk about different types, but it's not an easy subject to describe, other than it has the ability to do work. That's what energy does. When work is done, energy is transferred. That's important. We're gonna pick up on that topic again later, that you cannot create or destroy energy. All you can do is transfer it. All right? So let's get back to work. Now, if you have a force parallel to displacement, so F equals force, D equals displacement. If they're parallel, then the cosine of the angle, there is no angle, the cosine of 0 equals 1. So you could just use the equation, work equals force times distance, because cosine of the angle 0 is 1. So that's why I didn't mention it earlier. However, if you do have an angle, let's give this an angle. The angle equals 30. Well, the cosine of 30 equals 0.866. So you're going to multiply basically your work by 0.866 because not all of the applied force is going in the direction of the displacement. Only 0.866 of it is. So that's why you have to multiply by cosine of the angle 30. So in this situation you say work equals force times distance times the cosine of the angle 30 in this situation. I haven't given you any numbers. I just wanted to point out the importance of work is force in the direction of the displacement. See, it's not all of it is in the direction, so we have to multiply by the cosine of the angle. Now in this situation we have force. So here's displacement. Hopefully I recognize that this is displacement, this is displacement, this is displacement, this is force. Force is in the opposite direction. So the angle for a straight line is 180. So we have an angle. The angle here is 180. So the cosine of 180 it equals -1. So in this situation we're doing negative work. So if the direction of force is in the opposite direction of displacement, that's supposed to be displacement, then you're doing negative work. Right? So can you do negative work? Sure. Yeah, you can do negative work. Now, what if force is, here's our displacement, here's our force, 90 degrees. Our angle happens to be 90. Well, the cosine of 90 equals 0. So you're doing no work because you're going to multiply force times distance times 0. So the work is going to be 0. So there's no work. So it's going to be 0. And that's what I was trying to emphasize, that the force has to be in the direction of the displacement or no work. I tried to explain that earlier. All right, so let's try an example. Let's try an example. How about if we turn to page 162. 162, practice A. A tugboat pulls a ship with a constant net horizontal force of 5 times 10 to the 3rd newtons. So we've got ourselves a lovely tugboat, and this tugboat pulls a ship apparently. So here's our ship. This is pulling the ship with 5 times 10 to the 3rd newtons. Okay. Then the displacement is 3 kilometers. So our D equals 3 kilometers. All right. Well, it's simple enough. The only problem is that you have to remember that we have to use meters because we know that the units for work is Newton meters. So, and the displacement and the force are parallel to one another. So cosine of the 0 is 1. So we really don't have to worry about that. But we could write it in the equation anyway. Force equals displacement times cosine of the 0 degree angle, and that's going to be Newton meters. So meters is the key there. So we're just going to take 5 times 10 to the 3rd times 3 times 10 to the 3rd, and that's going to be 1.5 times 10 to the 1.5 times 10 to the 7th joules. All right. So 5 times 10 to the 3rd is these are our newtons. I should be writing my units down, and these are meters. We can't use kilometers. So those of you who are wondering where this number came from, I can't use kilometers. I got to use meters because joules is only interested in meters. I just moved the decimals all I did. All right. So, let's try practice number 3. Practice 2 is the same. There's no angle, there isn't anything. In practice 2, the reason I'm like practice 3 is a shopper in a supermarket pushes a cart with a force of 35 newtons, and we have an angle of 25 degrees. So here's our exasperated shopper pushing the buggy, and the buggy and the angle we have here, and here's our exasperated shopper. We have an angle, so this angle here equals 25 degrees. Well, now we're going to have to plug that into our equation, aren't we? Let's see. We need a displacement. The displacement is 50 meters. So that's in meters. We don't have to worry about that. That's in meters. And the force equals 35 newtons. Well, all we really have to do is multiply this out, plug it all in. Work equals 35 newtons times 50 meters times cosine of the angle 25, and that should be work equals 1.6 times 10 to the third joules. Right. Okay, one more. We could do number 4. A 2 joules of work is done to raise a 180 gram apple. How far was it lifted? Well, this is number 4. I'm on page 162. Work equals force times distance times cosine of the angle theta. Well, we have force and we have displacement without an angle. They're both going up, so that's going to be 0. That's going to be 1. It's not really going to play a role here. But what we have joules and we have newtons. So we have newtons and we have joules. So, and what we want are distance, and distance is in meters. All right. Sorry, these are the units. And so whenever we're looking for meters, and we have newtons and we have joules, therefore what we're going to have to do is we're going to have to take our 2 joules and divide it by the newtons, because we were given a 180 gram apple. Well, we need kilometers. We need newtons. So we got to turn this into kilograms by moving it 3 places to the left. So 0.18. We have to move it 3 places to turn that into kilograms, because newtons can only work with kilograms. And then we have to multiply that by 9.81 meters per second squared in order to turn that into a newton. All right, because it's a force. We're looking for force of gravity for that apple. So that's why we divide this by 0.18 times 9.81 is 1.76. 1.76, and those are newtons, and that'll give us meters, because remember there's newtons and joules, because these are joules per meters, and the only thing that falls out is meters, and that would be 1.1 meter. Alright? Good question.